Circles. This is a very important topic of class 10. It is a continuation of the geometry that you have been learning in classes 7, 8 and 9, which means that you will require the prior knowledge of parallel lines, triangles and quadrilaterals. So before we go into the sums of circles related to circles, let us try and understand the basics of circles. Chord and the perpendicular distance from the center of the circle. Here I have the chord AB and I am drawing a perpendicular from the center of the circle, perpendicular to the chord AB. What is the relationship between the two of them? So, if I have, here we have that OM is perpendicular to AB, then it implies that AM is equal to BM. And the converse will be, if AM is equal to BM, then it implies that OM is perpendicular to AB. Here it's a very simple proof. You can prove the two triangles. Triangle AO, triangle AOM is congruent to triangle BOM by RHS, and which will imply that this implies that AM is equal to BM. So this implies that M is the midpoint of chord AB. So here we are saying that if you have a chord AB and you draw a perpendicular from the center of the circle, if it is a perpendicular, you are always meeting the midpoint of AB, and if you are joining the center of the circle with the midpoint, then that OM is always going to be perpendicular to AB. Chords and distances from the center of the circle. Observe this properly. In this circle, you have AB and CD. Both AB and CD are equal. It implies that the perpendicular distances, that is OM and ON, are going to be equal. Converse will be, if the perpendicular distances are equal, then the chords are also going to be equal. In the second figure, you have AB is a chord which is bigger than the chord CD. Then it will imply that the perpendicular distance OM is smaller than the perpendicular distance ON. Obviously, if the chord is bigger, it is going to be closer to the center of the circle. And if the chord is small, it is going to be away from the center of the circle. Arc and its properties. I have a circle with the center O and there is a chord AB whose endpoints are A and B. This chord AB is dividing the circle into two parts. One part is arc APB and the other part is arc AQB. Since arc APB is smaller than the arc AQB, we call that arc APB is the minor arc and arc AQB, and therefore arc AQB is going to become the major arc. Understand that here you are talking about only the circumference of the circle. Now what happens to the interior of the circle? So I have a circle with a chord AB whose endpoints are A and B. This chord AB is dividing the interior of the circle into two parts. This minor part, the smaller part is called the minor segment, and the bigger area is called the major segment. I have a circle with center O, this and 2 points A and B. If I join the 2 points A and B along the circumference of the circle, I am getting an arc APB. If I join A and B as a straight line like a chord, then you get a chord AB with endpoints AB. And if I take the join the point from A to the center of the circle, from O to the point B, I am getting an angle AOB. Observe that arc APB, chord AB and the angle AOB, all three have the same endpoints A and B. Angles made by an arc and segment. So look at the arc APB. The endpoints are A and B. Now if I join AB, you will get a chord AB. So whether I say arc APB or chord AB, both of them have the endpoints A and B. The angle subtended by the chord AB at the center is going to be angle AOB, and the angle subtended by the chord AB on the circumference of the circle is going to be angle APB. The relation between angle AOB and APB is angle AOB is equal to 2 times angle APB. The condition is that this chord is dividing the circle into two parts. So both the angle at the center and angle on the circumference have to be on the same side of the chord. In that situation, angle AOB is equal to 2 times angle APB. So remember, the condition has to be that angle AOB and angle APB, both of them have to be on the same side of the chord AB. Now let us understand this one. If I take chord AB, this angle AOB would have been this, angle AOB would have been this. But no, I am looking at the relationship, I am looking at the reflex angle AOB. Reflex angle AOB. You see the chord AB, you have one angle on this side and the other angle on this side. So in such situation, you will look at the reflex angle AOB. This reflex angle AOB is 2 times the angle APB. Angles in the same segment. So suppose that there is a chord AB and the chord AB is subtending an angle at the center, which is angle AOB, and the same chord AB is also subtending another angle on the circumference, angle APB. In that situation, you know that angle AOB is 2 times the angle on the circumference. But suppose that there was one more angle with the same endpoints, that is like this, A and B, with the same endpoints A and B. So you have angle AOB, that is angle on the subtended at the center. Then you have angle APB, which is the angle on the circumference. And suppose I have one more angle, that is angle AQB. You observe that this also has the same endpoints A and B. So we know that angle APB is equal to half of angle AOB. In the same way, we also know that angle AQB is equal to half of angle AOB. This implies that angle APB is equal to angle AQB. We call such angles as angles in the same segment. Chords, arcs, and angles. In one of the slides before, I have explained to you what is the relationship between a chord and the perpendicular distance between the center of the circle and the midpoint of the chord. Now in this circle, we are talking about chords, arcs, and angles. So this AB and CD are the arcs. This AB and this line segment AB and line segment CD become the chords. And you have the angle over here, that is angle AOB and angle COD. So if arc AB is equal to arc CD, that is the length of arc AB is equal to length of the arc CD, then it implies that the line segment chord AB is going to be equal to the line segment chord CD, and it further implies that angle AOB is equal to angle COD. If AB is to CD, that is the length of AB is to length of CD, the ratio of the length of AB and CD is equal to 1:2, then the angle between them, that is angle AOB, is equal to ratio of angle AOB and angle COD is equal to 1:2. Now that we have understood the basics of a circle, let us go one step ahead, that is we are combining a circle and a quadrilateral. So we are looking at a quadrilateral whose vertices are lying on the circumference of the circle. A quadrilateral whose vertices lie on the circumference of the circle is called a cyclic quadrilateral. So you can see over here that the quadrilateral is inscribed inside the circle, or you can also say the circle is circumscribed. The vertices of a cyclic quadrilateral are called concyclic points. Now there is a wonderful property of a cyclic quadrilateral, and which is that the opposite angles of a cyclic quadrilateral are supplementary. So if I know angle C, I can find out what is the angle A, and if I know angle B, then I can find out angle D. So angle A plus angle C is equal to 180, and angle B plus angle D is equal to 180. Now, if I extend one of the side, so if I extend one of the side, that is, suppose I extend this way, that means I'm having over like this, so which is A, B, C, D, one of the sides is extended outwards. I am getting an angle over here. One of the sides is extended outwards like this, so I'm getting an angle over here. This is called the exterior angle. Just like you had for a triangle, if I extend one of the sides, I'm going to get this becomes the exterior angle. This is the exterior angle. So in a triangle, you said that the exterior angle is equal to the sum of the two interior opposite angles. So you said exterior angle is equal to angle 1 plus angle 2. But in a cyclic quadrilateral, an exterior angle is equal to the interior opposite angle. Interior opposite angle meaning this angle. So you are saying exterior angle is equal to the interior opposite angle, which means angle BCE is equal to angle BAD. So I may expand, if I extend it on this side, that is if I extend it like this, then this angle will be equal to the interior opposite angle, that is angle D over here. Tangents and secants. So here I have a circle and a line. What is the relationship between the circle and the line? This is a straight line. The first one is that the circle and the line have no point of contact. So there is no relationship. Here there is one single point of contact, Such lines are called tangents. When a line and a circle intersect at 2 points, then there are 2 points of contact, and such lines are called secants. So this is a secant and this is a tangent. Theorems on tangents and intersecting chords. So here I have a circle and PT is the tangent. The point of contact of the circle and the line is P. So the first theorem says that when I join the center of the circle to the point of contact, this OP is the shortest distance. Meaning if I draw like this is not going to be the shortest distance because this is not going to be the perpendicular distance. So OP, the perpendicular distance over here, OP is perpendicular to PT. Remember, we are talking about at the point of contact. So the distance between the center of the circle to the point of contact is going to be the shortest distance. Now suppose that you have two chords like this, two tangents like this, sorry. These are two tangents, one is AP and the other is BP. So there is a point outside the circle. So you are drawing two tangents and these are the two tangents AP and BP. Now this is very important. You observe over here that from this particular theorem, you get that OA and OB are going to be perpendicular to the tangent. OA and OB are going to be perpendicular to the tangent. So if you observe the two triangles, that is triangle OAP and triangle OBP, these two triangles are going to be congruent. Congruent because you have a right angle over here. You have the hypotenuse which is common, and you have the radii which will give you the side. So by RHS, you are saying triangle OAP is congruent to triangle OBP. That will imply that AP is equal to BP. So AP is equal to BP. So the next theorem tells us that when tangents are drawn from a point outside the circle, so when tangents are drawn from a point outside the circle, that is if I have a circle like this and if I have a point over here, and if I draw a tangent like this, another tangent like this, these two tangents are going to be of equal length, that is AP is equal to BP. The next theorem is talking about you have two circles. They may be of the same radii, or they may be of different radii. But if you have two circles which are touching each other externally meaning that there is one common line like this, one common tangent. So you observe that this is going to be perpendicular distance and this is also going to be perpendicular. So AP is perpendicular to the tangent and BP is also going to be perpendicular to the tangent. So this AP plus BP will give you the distance between the two radii, that is AB. But if the circles are touching each other internally, then AP is again going to be perpendicular distance and BP is also going to be perpendicular distance, and you will get the distance between the centers of the two circles by doing AP minus BP. That is AP minus BP will give you the distance between the two centers. Here the distance between the two centers you will get by adding them, that is AP plus BP. Direct common tangents and transverse common tangents. You have two circles over here and tangents like this. You see that these two tangents are called the direct common tangents. But when the tangents are going in a cross like this, then these two tangents are called transverse common tangents. Here, let us understand the relationship between the chords when they are intersecting internally and when they are intersecting externally. This is, you have two chords, that is chord AB and chord CD, are intersecting internally inside the circle. And here the chords, that is AB and CD, are intersecting externally. So they are both coming like this. Here I have a chord, that is a secant, and this is a tangent. You observe that this is a chord that is going till here and a tangent like this. These are both a secant and a tangent which are intersecting externally. Let us see what is the relationship over here. If you look over here, they are intersecting at the point P over here. They are intersecting at the point P over here. They are intersecting at the point P over here. So we have over here triangle APC is similar to triangle DPB. You can see this because these two are angles in the same segment. That is, this is angle APB and angle CDB. So this is angle CAB and CDB. Both the endpoints are the same, and therefore these two angles are equal. In the same way, you have these two angles are equal and alternate vertically opposite angles. Therefore, triangle APC is similar to triangle DPB by AA postulate. When you write down the ratios, you get PA into PB is equal to PC into PD. Now, how do you remember this? This can get confusing, right? So I will explain to you how to remember that. Let us first understand this and this also. Here I have a triangle ACP, and I have another triangle that is DBP. You remember we had done that is the exterior angle is equal to the interior opposite angle. So A is equal to D over here. That is angle BDP. And this angle is equal to interior opposite angle over here. So again we are getting triangle PAC is congruent to similar to triangle PDB. When I write down the ratios, again I'm getting PA into PB is equal to PC into PD. I will explain that later on again. Now here I am, we have a secant and a tangent. In this also triangle PAT is similar to triangle PTB, which gives us PA into PB is equal to PT square. How to remember is what I'm explaining now. You observe the chords AB and CD, chords AB and CD, chords AB, and you have the other one as a tangent. They are intersecting at the point P, intersecting at the point P, intersecting at the point P. P from the point of intersection to one end of the chord PA, then from the point of intersection to the other end of the same chord PA into PB is equal to from the intersecting point to one end of the other chord into intersecting point to the other end of the second chord, that is PC into PD. Same way over here also. Intersecting point PA into PB is equal to PC into PD. Over here, PA into PB is equal to, there is only one PT. So that is equal to PT into PT square. Angles in alternate segments. So first of all, let us understand what are alternate segments. So if I have a circle like this and I have a tangent over here, then, and suppose I draw a chord over here, that is, suppose this is BA and this is P and Q, you observe that the a circle is being divided into two segments. One is the yellow segment and the other is the purple segment. So when I'm talking about alternate segments, I'm first one angle will be angled by the chord with the tangent, that is this angle. And in the alternate segment, that means I have to look at an angle like this. This will become the angle in the alternate segment. So over here, this is the angle made by the chord with the tangent. Then if this angle is going to be equal to the angle made by the chord in the other segment, that is angle BCA and angle BDA. So you have angle BAQ is equal to angle BCA, and in the same way angle BAQ is also equal to angle BDA. Of course, we also know that these two angles are angles in the same segment. So don't get confused like that, but these two angles are going to be equal, and these two angles are also equal to the angle in the alternate segment. Here I am looking at this angle, that is this angle if I look now at this angle made by the chord, with this side of the tangent, that is this angle, then I have to look at the alternate segment, because since this angle is in this segment, we have to look at the alternate segment, meaning I go to this side. That means angle BAP is equal to angle BCA.